Professor Kai Wünnemann to give his talk on the impact cratering process. And Professor Kai Wünnemann, he is working at the Museum of Natural History, right? Am I right? Or Natural Science, Naturkunde, yeah, in Berlin. And then he's an expert, we're expert on cratering, on simulation, and he, as you might have heard, that he is also very good in comparing the simulation results with experimental results. And so today he is only given the first part, giving the fundamentals, as he said, on the impact process. And he promised us already that he'll give another talk. Okay, Kai, it's all yours now.
Yeah, good morning, everybody. It's a great pleasure to be here, and thank you very much for the invitation. I very much enjoy talking about impact cratering, which is very close to my heart, as you can imagine. So I hope that I can get as many as possible of you interested in this very important aspect in the solar system, I guess. I prepared this more as some sort of a lecture or seminar, giving you insights into the process itself, but I will certainly focus on the moon. And yeah, and the moon is basically maybe also one of the best examples for studying impact cratering, because when you look at the moon, the first thing you basically see are impact craters. There is more than this, but I guess the surface of the moon is clearly dominated by this process, and that kind of illustrates how the importance of this process in the entire evolution of the solar system, that while we look on Earth, we hardly see any craters. All other planetary surfaces are covered with these impact processes, and that basically explains much better how often that actually happens and what sort of a dominating process is probably in the evolution of the solar system. Okay, this slide basically shows something what I want to show you. As Wing said already, I'm more an expert into numerical modeling, so many of the things I will show to you today are guided by numerical models, but I have also a lot of experimental results, which I will also present here to explain the process and give you insights, and maybe also some guides or some directions in terms of literature, relevant literature. So let me see how that goes on. Here we go. Yeah, as I said, the lunar surface is covered with craters. This is a bit of an older picture. We have now much nicer ones. This is from Apollo mission. But nevertheless, when you look at this, you basically see the same thing as you see today. You see craters, as I said, and the next thing, when you will have a little bit closer look at all of these craters, you see that they are different in terms of their morphology. So you have these sort of pits, these bowl-shaped craters. These are the clearly, or the most of the craters by far have this sort of morphology. This is what one would understand when we talk actually about a crater. It's bowl-shaped. It has, can you actually see my mouse? I suppose so, yeah. So you see this bowl-shaped structure. You see a raised rim. They tend to be smaller. The depth diameter ratio of these craters is about 1/4 to 1/5, roughly. And you notice loads of them. This is what we call a simple crater. Well, it looks like a simple bowl-shaped structure. But when we study these sort of craters, and as I said, they're not so easy to find on Earth, but we assume that the process and the morphology is more or less roughly the same. So if we study these craters on Earth, we have much better possibilities to look at how the crater subsurface actually looks like, yeah. And this is a cross-section that is based on studying terrestrial craters. And then apart from the surface expression, where you have this raised rim and so on, we see that the inner part of the crater is filled with some what we call a breccia lens. Inside this breccia lens, you may also find molten rock lenses in there. But that's something we would only know from studying craters on Earth. This is nothing we can see directly on the moon, but we expect that this is also collapsed material that was flowing into the crater somehow during the crater formation process. It's maybe also important to note that these simple craters only occur up to a certain size. Yeah, there's some sort of a threshold. I call that here DC. That is the threshold diameter. As you see in the next slide, I think it's about 15 kilometers. So roughly all craters smaller than, let's say, 10 to 16, 17 kilometers, 12 to 16, 17 kilometers is rather sharp transition, but it's also a little bit gradual. So it's not precisely 15, but roughly 15 kilometers is what you may bear in mind. So all craters smaller than 15 kilometers have this simple crater morphology. Well, and I picked this picture because it has also another very important crater morphology. These are complex craters, and they're maybe not look as much as a crater what you may think of a crater. In particular, it has a very flat crater floor. So it's not really bowl shaped anymore. You see the what we consider as a terraced rim. So you have a part of the outer crater where material or towards the inner crater you're going stairwise in steps and terraces into the inner part, and then the inner part is very flat. And then the other most striking observation is that in the center we have what we call a central peak. So something that is sticking out in the center. And as I said before, roughly craters larger than 15 kilometers have this, what we call complex crater morphology. The next step then, here we have also a cross-section for this complex crater morphology. Again, this is based on terrestrial craters. And what is important to note is that when we would be able to study this inner part, this central peak, then we see that this is composed of material that is coming from deep underneath. Yeah, so it's not material that is sliding inwards and then colliding in the center and is then kind of making this or forming this central peak. It is material that is transported from deep underneath going up to the surface. The flat inner part is, we expect that there's probably melt underneath, but maybe also some breccias. And this is this stepped or terraced crater rim. You see these terraces, normal faults, maybe also listric faults. That's something we could be discussed. But you see that there are big blocks, fragments that have been moved inwards. This is roughly the structure of complex craters. So when we go even bigger, we know there's maybe some step in between where we have peak ring craters or so, where the central peak is not really a central mount, but a ring. But are making right away the step to larger craters or basins, what we call them, and then actually peak or multi-ring basins. And they usually occur starting, so peak ring craters on the moon larger than 200 kilometers, multi-ring basins larger than 600 kilometers in diameter. But the number of such craters, or basins, I should better say, is much smaller now. So maybe about 80. There's a bit of a discussion because not all of them are so nicely preserved as the Orientale Basin, which is one of the youngest well-preserved large impact basins. You see here nicely these ring structures, several rings. Here are all the different radii. So this is not diameter, these are radii. So the outer crater rim is 460 in radius, so almost 1,000 kilometers in diameter, just to give you an idea of the dimensions. And on this picture, you also see nicely again these classic complex craters here and here and here. They're very nicely showing the morphology of complex craters again. So what I'm aiming at here in this lecture, or is it not going on, is to explain you the processes or better to say the sequence of processes that eventually result in the formation of these different crater morphologies on the moon. Basically, that also applies to all other planetary surfaces, if you will. Some of the the sort of parameters what we're talking about are more specific for the moon, but in principle, what I present here is applicable to all other craters as well. So obviously we start with some sort of a projectile, which may be an asteroid or a comet, or when we go to very big craters, there may be even differentiated planetesimals or something. Yeah, so the full range of different projectiles. Here I show that it's most likely that such an impact occurs at an angle. However, many of the things I will show you in a minute are more based on studying vertical impacts, which is not that much of a problem, but I will address this point also. So you impact the surface, the projectile penetrates into the target, and you generate a shock wave. That's very important. A shock wave that is traveling into the target. Here it goes on. Then some sort of a crater is formed or is excavated, what we call the transient crater. I will explain that also more in a minute. And material is ejected. So the crater is formed by ejection of material that is thrown out and displacement of material. So material is moved further deeper into the crater. And now the process kind of starts to separate. If this transient crater is larger than a certain threshold, I said at larger than about 15 kilometers, then we're going this path and we end up with this sort of complex crater structure, or if you will, also in a basin structure. If we are smaller than a certain threshold, we end up with a simple crater. And there's some sort of a modification process, how we get from this transient crater bowl-shaped morphology into this complex crater morphology and a simple crater morphology. The easiest to explain this process, it has been suggested already long ago, to separate this, and that's how I made also this sketch, into 3 stages: the contact and compression stage, the excavation stage, and the modification stage. However, you have to bear in mind that this is not a clear separation of stages. Usually one stage grades into the other, and it's you know, there may be parts in the crater where, you know, the excavation stage, for instance, is still ongoing, while at other parts of the crater modification has already started. Yeah, so it's not an absolutely clear separation. Okay, I will start with the contact and compression stage. This is a very old snapshot series of a simulation, but it still shows the process quite well. As I said, we look first at vertical impacts. That makes the thing somewhat simpler and the whole thing more symmetric. On the right-hand side, you see the density. On the left-hand side, I used here tracer particles showing the different materials. Yeah, so you see here in white what is initially the projectile, in green what is the target, and in this case the density of the projectile at the same as the target. 18 kilometers is the average velocity on Earth, but that also applies for the Earth-Moon system. The Moon has a slightly smaller average impact velocity than the Earth, but overall that's very similar. Other planets, the further away from the Sun, the smaller usually the average impact velocity. I'm saying average. You can have smaller ones. The smallest velocity is close to the escape velocity. The highest velocities tend to be in the Earth-Moon system, 40-50 kilometers, if I'm not mistaken. Okay, next step, as I've shown already in the sketch, you see that the impactor penetrates into the target, and you generate a shock wave. This shock wave is traveling upwards in the projectile and downwards into the target. This red is an increase in density. You see here, you easily double the density, and maybe even more than this. Yeah? So due to the shock, the material is extremely compressed. At some point, you see now how the crater rim evolves. Yeah? So material is partly ejected, but also partly uplifted. You see a lot of deformation ongoing, also in the projectile, of course, itself. And then at some point, the shock wave reaches here the free surface. We have a reflection, and the phase changes the phase. So we turn the shock wave into what we call a rarefraction or release wave, which then unloads the material from the shock. And this is what is going on here. You see that material has been unloaded significantly, and the shock wave further propagates into the target. And the unloading here actually you see that material's density is below the initial density already, which is best explained when you look at a phase diagram. Here you see specific volume, and this is pressure. And this phase diagram shows how shock wave, or basically explains different stages of shock. So this is what we call the Hougonneau curve. It's not a thermodynamic path. Let me stress this here right away. The Hougonneau curve basically connects different stages of shock compression. So if we start from here as an initial density or specific volume, and we jump up here to this shock pressure, then we follow an adiabatic release, which is the dashed blue line, and we end up here at the end in a liquid vapor field, which means that after the release from shock pressure, the material is either molten or even vaporized. Yeah, so you see that apparently shock compression is a non-isentropic process. We increase entropy by the shock compression, and depending on the pressure or the amount of entropy increase, you end up after the release in vaporization, melting, or other stages, solid phase transformation stages that may also occur. I usually, why I'm talking so much about shock pressures, because, you know, these are all things that we hardly observe on the moon, but the entire cratering process is actually driven by this shock compression. Here is a diagram showing distance versus particle velocity or temperature. You can apply it to both. Yeah? This is the shock front, so you have a very instantaneous increase in shock pressure. Then you have some sort of a shock plateau. So this is basically a profile through this contour plot in here. And then we have the release from shock pressure, which goes much slower. But what is most important is that after the shock pressure, the material has a higher temperature, what is kind of expressed in this diagram. So if the temperature is high enough, melting may occur, vaporization may occur. But what you also have, that material is in motion. So if you look at particle velocity, of course, you have a very, very high particle velocity upon shock compression. But even after release, if the material was before standing still, it gets into motion. And this motion is what we call the excavation flow. And that basically drives the excavation and the opening of the crater. So this is very important that only due to shock, we end up with craters that are 10 or 20 times larger than the projectile. When you have a low velocity impact where we don't generate a shock wave, we have only craters that are about 1 or 2 times the size of the projectile itself. That's the most important physical difference between hypervelocity impacts, when the velocity is larger than the speed of sound and we generate shock waves, versus sort of standard low velocity impact. That's important to bear in mind. So this is all what I want to say about compression stage. You know, we can talk a lot more in particular about the products, how you modify material, what melt and vapor looks like, and so on and so forth. But for the understanding of the rest, I think these are the most important things, how to understand the other 2 stages. And as I said, we have the excavation flow ongoing, and this is what drives the excavation, so the formation of the transient crater. And here I want to show you first some results from experiments. So these are first experiments. You know, you would consider, obviously, we need some sort of an accelerator. This is what we call a light gas gun, 2-stage light gas gun, basically, that allows us to accelerate projectiles. You know, depending on the size, this is a very big one at the EMI. This is here the Fraunhofer Institute in Germany. This is, I think, in full length, almost 40 meters long. you can accelerate here 5 to 10 kilometers per second, almost 1 centimeter steel projectiles, but you can also use meteorites and so on. And we used, of course, hard rocks. You would, in the first place, you would expect the moon is formed from some silicate material. This is what you would go with and test what happens if we shoot such a projectile onto a rock. This is a movie from high-speed camera showing this, and here on the right-hand side you see the numerical model. I'll let this go. And of course, this is not what we can observe with a high-speed camera, but afterwards we can cut the rock and look how the crater looks underneath. So we see a lot of fracturing here ongoing. That's in a way also very important when we use geophysical methods to study the crater. But we get some sort of a crater cavity, and that looks in a way somewhat similar what we see also in a numerical model. I hope you can see these movies well through the virtual presentation here. I don't know how well this is transmitted. Okay, when we look at this, this is the outcome from above on this sort of a block, what the crater looks like. This is the cross section. But when we compare it with the morphologies that what we just talked about, so this bowl-shaped simple crater morphology or this complex terraced central peak crater morphology, they don't have anything in common. So what's wrong here? Well, the most important thing what is wrong here is that rocks are strong. They have a certain strength. And on the small scale of a laboratory experiment, gravity doesn't really play a role in these experiments. But when we go to larger scale, gravity becomes more and more important. So if we want to reproduce this sort of a thing in the lab, we have to balance the strengths versus the gravity forces to make anything something similar. As it is difficult to vary gravity, what we use, we decrease strengths accordingly. Yeah. So in another experimental series, I want to show you results using granular material. So material with very low strength. That's then easier, or this is the way how to balance the forces and get something which looks more similar. Fortunately, granular material, in this case, it was quartz and semolina, and we used also other materials. They have a low speed of sound, so the impact velocity does not have to be that high. I think in this experiment it was about kilometer per second. And though that's a lot less effort in terms of the accelerator that you can use. This is a high-speed movie. What we do here is a quarter space experiment. So maybe I go back again. You see here a window, and we shoot along this window, and then we can see how the crater forms. And we basically form only half of the crater. So we have a half space, and from the half space, only half of it. So we end up what we call a quarter space experiment. And here you see that in steps. So at the very beginning, you see some sort of a flash and the penetration of the projectile, the very beginning of the crater formation. And then we can go on and see how the crater further forms. This is now running at much faster. And we end up at a point where we have some sort of a maximum crater depth. And when we let it go on, we see a little bit later that we end up with a maximum crater diameter. And actually this sort of a construct is what we call then the transient crater. So this is the maximum cavity that is formed due to shock excavation. Yeah, so through the excavation flow that results from the shock wave. When the crater now maybe gets even bigger or any sort of other modification processes, they are due to what I mentioned in the beginning, due to modification. They're not due to the shock-induced excavation. They don't contribute to the size of the transient crater. And therefore, the transient crater is a good measure of the impact energy. Here, I'll let it go to the very end. You see at the end, the final crater is a little bit bigger than the transient crater. It's about 25% larger. That varies a little bit, depends also a bit on gravity. And these are the profiles of these two stages you can compare. And when you compare such a crater, then also in terms of its ratios and everything, with a typical simple crater on the moon, this is the Moltke crater, you see quite a nice relation. Yeah? So we are able to reproduce the formation of a simple crater in a laboratory by using granular material, reducing strengths, and then we end up with something very similar. This is what running this sort of experiment then also allows us to make predictions, what is put into something so-called scaling laws. In the literature, you find this among the name pi group scaling, and that goes back, well, actually it comes from explosion cratering, but relating it to or using the same mathematical approach for impact cratering has been done by Schmidt and Hausen and Holzapfel. So basically Hausen and Holzapfel are the two guys who developed this a lot and run loads of experiments to calibrate our scaling laws in this. So you could also say the Hausen and Holzapfel scaling instead of pi group scaling, I think. So here I show you the results. This is from our experiments here in sand and semolina. They all fall at 1 dot because it was very difficult in these experiments to vary the parameters. This is what is a gravity scaled size. So when we have an average velocity and gravity remains the same, this is basically the size of the projectile. And this is basically the scaled diameter. So this is the diameter of the crater over the diameter of the projectile. Density ratios we don't consider here. There's another experimental series. I just used the slide that I had at hand here from Jens Olmö. We did experiments in a laboratory in Madrid. And then we added also some of the Holzapfel and Hausen data. And then you see that all falls nicely on a line. This is a double logarithmic scale, and you come up with some sort of simple power law. You can further complicate it, taking other properties into account here. But in principle, this is what it looks like. So pi d, the scaled crater size, is given by some factor k here, k2 given, times pi 2, which is the gravity scaled size, to some exponent that is given by this ratio with this mu parameter, but I don't want to further go into detail with this. Here these scales are given. Here I've also put a scale here for Earth and for Moon, assuming a certain average impact velocity and gravity, and then you can translate this x-axis directly into projectile diameters. Yeah? And then you see how you can translate basically an experiment from a laboratory scale, so with a much lower velocity, and then see that directly relates to a crater or an impact of a certain size here, some 10s or 20s, or for the Moon, that would be even larger impactors, forming similar craters, similar in scale. However, these experiments are limited, so we can only go to a certain size range. To go further than this and be much more flexible in terms of the parameter choices, it's very convenient to use numerical modeling. And this is what we've done here. For instance, for sand, you see all these green dots, they nicely fall on the same line. You can then study different materials. This is done for water. You see the line is slightly shifted. The exact slope and position of this line depends on material properties. This is strength, friction, porosity, density, composition, all sorts of these things you can test, and then you get different scaling lines. And when the material gets too strong, it becomes independent of gravity, and then it flattens out. And these are the results from these experiments I showed you in the beginning, from these sandstone blocks at a small scale. Okay, however, this is all very homogeneous targets. In real life, we have to consider also layering, which may be also important. And here I show you an experiment, which when we carried it out, also the results came a bit of a surprise to me. Here you see what you can consider as layers. In fact, this is a cacao powder. You use sometimes funny materials in experiments just to use something with certain properties. But here the aim was actually just to use the cacao powder layers, these are these dark ones here, as kind of tracers. We wanted to see how the target actually deforms upon impact. And I show you what came out of this experiment. You see here some shaking from the glass that is not of really importance, but you see that we get something like what you can call a nested crater, or a concentric crater, what it is often called. So you have a crater morphology, you have this plateau, and another crater sitting in here. And I think in this particular case, it was mostly due to the fact that this cacao powder was, you know, cacao is a bit oily and the material can glide very easily over it. So it acted actually a little bit as a glide horizon, that material was more easy to transport outwards than downwards into it. And only when it overcome a certain threshold, another crater started to form. So there are two things when layering becomes important. That is, on the one side, when you have density contrast. So for instance, for the moon, that would apply to the fact that you have, and I know you have heard some seminars on this already before, you have some sort of a loose regolith layer sitting over some mega regolith, and underneath maybe some more competent basement rocks. Then you would have mostly a density contrast due to the different degrees of porosity, but due to the different degrees of fracturing, you have also a contrast in strengths, which affects also the morphology and the formation of craters in here. So we studied this also by numerical molds. And again, you can do that there a little bit more systematic. So we set up something with typical properties for regolith and mega regoliths and basement rocks. This is the profiles for strengths, for density, and for porosity. And when you assume just the pure regolith, this is the brown line here, you get a nice line very similar to the ones in sand. When you have the competent rocks, so this is here the basement material, you get this blue line that at the small scale, you have purely strength-dominated craters, the ones that you've seen also in the sandstone lab experiments. And then it kind of bends over into a similar behavior as the granular material with a slightly different slope. But when you have this sandwich package here, then you get this green line. So you get this sort of bumps here in the scaling line, where we get this nested or circular crater morphology at each of these bumps. So in other words, scaling is something that we can do relatively well if we have homogeneous targets. When layer targets comes into play, unfortunately, the scaling line doesn't work so well anymore. So that is something that we have not really parameterized yet. It is just, you know, how irregular this line basically looks like. Okay, bear in mind that all this scaling, all these estimates of crater size basically only applies to the transient crater, which is not what we see today. That's only an intermediate step. We are not yet at the final stage, the crater modification stage. Final thing about the excavation stage is the ejection of material. So this shows a cross-section, and you see these trajectories. The trajectories show how material is displaced along these banded trajectories. And you see this is the zone where material is just displaced, so it is transported into the subsurface. But when these lines end above the surface, that basically means that the material is actually ejected. So it's thrown out of the crater and then more or less on a ballistic trajectory and lands at some distance. And the zone where material is ejected, it's a bit misleading, and the terminology here is not chosen very well in my opinion, but we call that the excavated zone. So this is about 1/10 of the diameter of the transient crater in depth. This is where material is ejected from, and underneath material is displaced. Yeah. The color contours here in the back show the pressure contours. So obviously you see that you have a lot of material that has undergone high pressure that is ejected, but you have also low pressure material that is ejected. So in the end, in the ejector, you find the full range, but you only find material up to a certain depth. Yeah. So if material underneath this sort of roughly 1/10 of the transient crater diameter, you won't find in the ejecta. That's going deeper into the target. Yeah, this is something you can also study in experiments. This is very old experiments from my close colleague Dieter Stoeffler from 1975, using here colored layers to study how ejecta is distributed. And then more recently, we reused these experimental results to study the ejecta again. So these are all modeled crater profiles through the results from craters. This is how you study the actual dynamics. So I've put here some literature from Chintala, Anderson, Hermelin, Pete Schultz, and so on. So there's a bulk of literature on this, where you use particle image velocimetry. So there you can, with this method, you can actually track the individual particles when they are ejected, and you can measure the angle and the velocity of ejection. And then you end up with something like this. So this is a cloud of measurements of ejection angle as a function of distance. So the launch position, this is the crater center, and this is normalized by the projectile radius, I think. And this is then what you get from models. So you can nicely calibrate then your models here and see how well they fit with the experimental observation. Of course, this is a bit of a cloud. It's a bit scattered here, the angle. It's less scattered when you look at the ejection velocity. But that also shows a bit that you don't have a well sorting of material by the ejection. Yeah? So when you look at the different shock stages, you kind of mix that all up in the ejecta. And roughly speaking, the highest shock material will be ejected the furthest. So at large distances, you find a lot of melt in the ejecta. Closer to the crater, the material tends to be less shocked and maybe larger fragments, but that's all. You know, it's not, you may also find melts or highly shocked material close to the crater rim, but it's much more rare. All these ejection angle and velocity, the angle is roughly about 45 degrees, but these parameters in principle strongly depend on target properties like porosity, strength, density, and so on and so forth. Yeah. There are also scaling laws that allow us to estimate the angle and velocity as a function of distance. And then you can use these results to work out the thickness of the ejecta layer. You know, this material, when it is thrown out, lands at some distance and form this sort of ejecta blanket. Here it is just shown for two different cases. It doesn't really matter. But you see that this follows the thickness of the layer, follows some sort of a power law. Here it's actually the ejected mass, but you can also translate it into a thickness. And this power law is about to the power of 3. Something 2.5 to 3 is what it is usually comes up with. Okay, these are the processes that dominate the excavation stage. And now I want to get to the what we call the modification stage. And obviously we touched this already for simple craters, so I won't go any further into this, where, you know, the formation of a final crater in terms of a simple crater is very straightforward. It's very close to the transient crater. It only gets a little bit bigger by material slumping inward. But the morphology, the formation of the complex crater morphology maybe is a little more puzzling. Yeah, here again, the morphology, central peak, flat crater floor, terraced rim. How does that actually form? And unfortunately, this is something that we cannot do in models. We had to extremely increase gravity at very low strengths. So that hasn't been really done with any sort of solid materials in a laboratory experiments. Of course, in fluid, that would work out, but that may become clear in a minute when I show you the results for this. So this is best done by using computer models. And here's a very simple setup. So we have here again our projectile, our target. These are just tracer lines showing you the modification, the displacement of material in the subsurface. And you see similar things as we've seen before. So you end up with some sort of a maximum depth of the crater. That would be the depth of the transient crater. Then this goes on, the crater starts to grow in lateral direction, so it gets bigger. That is something then to form the diameter of the transient crater. But you see at this stage already that the crater floor starts to uplift. Yeah, and that goes on. We have now the transient crater diameter reached, and when I let it on going, you see how here a central peak is formed and a relatively flat crater floor. You don't see the terrace rim in here, but that's more a numerical problem. You see that slightly here in the displacement of the tracers in it. So how does it form? You know, this is basically due to the fact that from underneath, for the given scale, the lithostatic pressure acting on the crater floor due to gravity is stronger than the strength of the material. So the crater floor starts to collapse and starts to rise and forming this central peak. So you can consider it as a buoyancy effect, if you will. You know, you have to consider that you form a crater that is many kilometers deep. So the stresses acting on the crater floor at this depth due to gravity usually overcome the strength of the material. As a side effect, the strength is certainly also reduced by all these fracturing and brecciation of the material as a consequence of the shock. The other important thing is you see that the final crater in this case is much bigger than the transient crater. It's not just 20% or something as we've seen in the simple crater case. So here I've summarized this in the different size cases. So this is what we started with when we looked at hard rock on a laboratory scale. The final crater is the same size as the transient crater. This is what we call a strength-dominated crater. All processes here are ruled by strength, and gravity is absolutely negligible in this case. When we go to larger scale, or if we decrease strength, yeah, as I've shown you in sand, but going to a larger scale, keeping rocks, we get to gravity-dominated craters. So the crater size is now controlled by the gravity or the lithostatic pressure in the target. But in the first stage, we end up with simple craters. So the deformation or the modification from the transient crater to the final crater is only this sort of material that collapses inward and forms this transient craterlets, about 20% change. And then we have these complex craters. For the moon, the crater is larger than 15 kilometers. Then we have this a lot more pronounced collapse process where material from deep underneath is uplifted and forms the central peak, flat crater floor, and so forth. Yeah? So the final crater then is much larger than the transient crater diameter. I don't show this here, but scaling, you know, predicting for a given impact energy, the size of the resulting crater is then some sort of a two-step process. First, you would use this pi group scaling to estimate the transient crater diameter, blue D here. And then you use a second scaling law that translate the transient crater and the final crater size. And there you have to say whether you predict a simple or a complex crater. This is not very well established, this scaling. There is a bunch of literature here that is based on observations or mostly actually on observations by Bill McKinnon and Schenk. I put here this more recent paper from Krüger et al. In there you have a collection of different attempts how to predict the transient crater size. We've been using numerical models also to try to estimate this. However, this collapse process depends on so many parameters that are not very well known. That's the reason why this sort of scaling approach is difficult in here. Okay, and then I promised that crater modification, the impact angle is also something that may matter or not. So I'll show you also a numerical model of an oblique impact. And there you see that you basically end up with very similar things. You have a transient crater. Of course, the ejection of material is asymmetric and different to a vertical impact. But the transient crater size is very symmetric and very similar to the one when you have a vertical impact. And that's basically due to the fact that the crater is formed by shock wave. Yeah, so you kind of inject the energy, and then this energy is distributed more like a point source, so more like an explosion. That's where this analogy is coming from explosion cratering and impact cratering. In both cases, you form more or less symmetric shock waves, and they are the main mechanism to excavate the crater. And then we can let this go on. You see then some asymmetries as a consequence of impact angle in the deeper crater structure, but overall, it doesn't look so symmetric when you look at it on a cross section, but I haven't a picture here now, but when you look at plane, you would see that the structure is very symmetric. Yeah, so with this, then you have a nice relationship between the impact properties with the scaling law, and you can estimate crater size and morphology. And that's very important. You know, you've heard lectures before on crater chronology, so dating impact surfaces by the size frequency distribution of craters. If you want to calibrate this, these scaling laws are absolutely key, because they allow to translate a given impact of flux in a size frequency distribution on a planetary surfaces. So that's very important to reconstruct the bombardment history, and also a key thing if you want to figure out how the bombardment history changed with time. So, you know, there are different models. Some people proposed late heavy bombardment, which came out of fashion now lately. So we're now thinking about more some sort of an exponential decay, maybe a bit spiky, but there's still a debate ongoing how the impact of flux changed, in particular during the early phase, what we consider as the late accretion phase. Yeah, I'm a little bit over time, but I still want to show you very briefly also how complex, how that all applies to basin structures. So here we have a picture I've shown already in the beginning, the picture of the Orientale Basin. So can we use this same approach to estimate the impact of size for the basins? Well, yes and no. In fact, we have to consider other parameters in there. And one key thing is that unfortunately there's only a much smaller number of basins preserved. They're so old mostly, and but we can use the gravity signature of these craters as well as an additional observation apart from the surface expression, which only gives us the morphology of those. And then we can combine these two things and try to work out the crater record for the moon and the size frequency distribution. So particular, what was the size of the large bodies forming these basins, which kind of ruled most of the processes, the sort of large scale processes effects on the evolution of the moon. Yeah, I don't know whether you've seen pictures like this before. This is based on work from Mark Wieczorek showing the Bouguer gravity anomaly of the moon. And you see for the big basin structures, these so-called mascons, or these mass concentrations. And that nicely shows where the basins actually are located. And this is also the reason why we actually now know that there are more basins than we can see at the surface. This was done also by Mark translating these gravity anomalies into crustal thicknesses. And you see the crust is thin where the basins occurs, and it varies also across the moon due to other reasons, but where we have basins, mostly we have a thin crust. Okay, how does it look like in our numerical models? This is the work I've done with Menghao Zhu from Macau University, showing maybe I show that again, showing the formation of the Orientale Basin. And here we consider another parameter, namely the temperature of the target. So when you look at these large basin structures, it's not negligible whether the target was cold or warm. You know, warm in the beginning, the moon is thought to be much warmer than it is now. So basins that formed early, we probably have to consider a much steeper temperature gradient, while in more younger basins, we can probably assume that the moon was rather cool. And comparing these two cases here, you see quite some differences. So you see how the central peak is formed. You get this some sort of an overshoot that collapses again. You get that actually several times. And this is how you form a rather flat inner basin structure. You see slight differences in the morphology. And that's something one needs to consider when we model basins. Here's a comparison of our model. This is the dashed line here for different cases with the crustal thickness models that have been worked out from the gravity anomalies. So this is the shaded gray and white. And you see there are some differences. So we have this sort of slab structure. So in our case, we predict in the models that this inner part sort of slightly collapses outwards, but that's not necessarily in disagreement with the gravity structure. You know, modeling gravity and coming up with these crustal thickness models are non-unique. So you can come up with different models. So we can also can compare directly the gravity signature. There are differences depending on the different crustal thicknesses or temperature models in comparison to the observed gravity anomaly. But this may be due to long-term effects. So a long-term isostatic relaxation may further adjust these differences that we get here in this comparison. Yeah, another thing I mentioned earlier, the ejection of material. If the ejecta layer from such large basin is preserved, which is more or less the case, at least in parts for Orientale, you can also use the thickness of the ejecta layer as a function of distance. This was observed by Fassett et al. Looking at craters. Some of them penetrated the ejecta layer, others didn't. And with this, Caleb estimated the thickness of the ejecta as a function of distance. This is shown in here. It's these different dashed lines he proposed. And from the models, we can also work out how much material is ejected. So another way how to calibrate our models with observations apart from gravity, the surface expression. Here also the ejecta was used. And then finally, you can try to make some sort of scaling laws. This is actually currently work in progress by a student of mine, showing the diameter of the Bouguer anomaly. So what we've seen before, versus the diameter of the transient crater. And you see here different cases. The different color plots here, spots here show craters that have been formed at different times. So we consider different temperatures of the target. And then you see that this affects slightly a little bit this relationship. So it's not entirely negligible, but overall you see nicely some sort of a trend in here. And when you know the transient crater, then you can use this sort of classical pi group scaling to estimate the impactor size. However, for this large scale, you know, we have to consider this sort of layered structure. So we have a mantle, a crust over a mantle, and that also affects the transient crater size. As you see here, it doesn't follow a nice power law trend as proposed in this simple experiments. Okay, with this, I want to close and maybe also lead over to the next seminar, which will be about the formation of the moon. I just want to briefly summarize here the big questions that remain, and some of them I would very much like to address in a follow-up seminar. So, of course, this is something you will deal with, I think, in the next lecture, the formation of the moon. So this is maybe the mother of all impact events, the collision of a Mars-sized body with the Earth forming the moon, which would be the beginning. However, it's not understood what's the fate of the impactor material. Very important question to understand the entire process. And yeah. And then something what we've been lately mostly dealing with is how does the impact flux affect the crystallization and the evolution of the magma ocean? So basically the distribution of melt. Was it generated or further extended the existence of a magma ocean by impacts? And then finally, we still need to understand the entire crater record, which basically means reconstructing old and very large basins, basin formation as the function of the thermal evolution, what I've just said, a better understanding of the gravity signature with the given crater record. So this is all required to reconstruct the entire crater record. Okay, and with this, I want to close. And thank you very much for the attention. And of course, sorry for going over.
Thank you so much. Even though you said it's just a beginner's lecture, but actually it's rather complicated, I tell you. One have to go back to look at it a couple of times to understand some of it.
Yeah, sure. It's I think it's available online, isn't it? Or
yeah. It'll be available.
Yeah, and I'm happy to answer questions if there is anything coming up.
So we have just one time for one question. Any question you have, please unmute yourself and ask the question. Anyone? If not, then maybe I ask this only question. You mentioned in your talk that the late heavy bombardment event theory is old-fashioned. Why is that?
That's it's not a short question, and it's a bit also about opinion. The idea was mostly born from the observation that it turned out that many of the Apollo samples have a very similar age. And from this, the idea was born that that was maybe due to a more intense bombardment, which was then called the late heavy bombardment. However, that may go under some sampling bias, as we only have now we have new samples. Maybe the from the Chinese mission will show something different. We'll see. But we have mostly these samples from the Apollo missions, which cover more or less the same area. And then relating these samples to basin structures is also not clear. There's been recently work also ongoing in the frame of our late accretion process by Tiantian Liu, making a more statistic approach how you can work out for a given sample location, how likely it is to find their melt from the formation of a certain basin. And this, again, in combination also with the age distribution you have in lunar meteorites, and so you find a much more scattered picture in terms of dating. The other thing is, you can come up with these n-body simulations of planet formation, and where you also get later on the cratering record, and you can twist these models to come up with a late heavy bombardment. But the more recent one actually predict that that may be not the case, and you may have some variations in the bombardment, so it may be a bit more spiky, but certainly or most likely not this sort of very pronounced intense bombardment period. That's in a nutshell. However, you can talk for hours just on this topic, whether there had been a late heavy bombardment or not. But now the vast majority in the community, I think, does not really believe in a late heavy bombardment anymore.
Okay, good. Maybe I sometime will ask Moby to give a talk.
Oh yeah. He would be one of the persons who could very well address this. I think Moby would be very, very good for this. But also from the sampling perspective, and I think maybe the now new samples from Changi Fort are very, very interesting to see whether they show other ages or what. We'll see.
Okay, guys, thank you so much. We will wait for your next talk. It will come very soon, I suppose. Sebastian. I hope you would listen to his talk also.
I'm very much interested. I will stay online if Sebastian doesn't mind.